Hello student, in previous lecture I have discussed about different type of compensation scheme. Now I will discuss about controller. So first I will discuss about PID controller. PID controller are commercially successful and widely used as controller in industries. For example, in a typical paper mill, there may be about 1500 controllers, and out of this 90% would be PID controller. Okay, so maximum use. So what type of controller are maximum use? PID controller. Okay, so the PID controller consists of a proportional mode, an integral mode, and a derivative mode. The first letter of these modes make up the name PID controller. Depending upon the application, one or more combination of these modes are used. For example, in a liquid control system where we want zero steady state error, a PI controller can be used, and in a temperature control system where zero steady state error is not specified, a simple P controller can be used. So depending on the mode of operation, we can use different combination of controller. That means we can use P controller, PI controller, PD controller or PID controller depending on the mode of operation. So the equation of a PID controller in time domain is given by like this: mt equal to kCET plus kc by Ti integration of 0 to t et dt plus kc td det dt, where kc is the proportional gain, Ti is the integral reset time, and Tt is the derivative time of the PID controller. Mt is the output of the controller and Et is the error signal. Okay, and this error signal we know Et equal to Rt minus Ct. The three different forms of representation of PID controller are shown in figure 2.55, where figure 2.55a shows the PID blocks and figure 2.55b shows the time domain forms of these blocks, and figure 2.55c shows the Laplace domain forms of these three blocks. Okay. The standard block diagram representation of a unity feedback system is shown in figure 2.56. Here the controller used is a PID controller represented by a block PID, and the system or plant is represented by GS. RS and DS are reference signal and disturbance signal respectively. YS, ES and MS are the output, error and controller output of the system respectively. For the purpose of good control, we require the system output YS to track any reference signal RS and at the same time reject or suppress deviation due to the disturbance signal DS. Okay. Now we will discuss this P control, proportional controller, integral controller, derivative controller one by one. Okay. So first we will discuss proportional controller. So this I have already discussed in proportional compensation scheme. So these are the same. Okay. So here see, a proportional controller has a proportional term alone. So the output of a proportional controller is proportional to the error Et, and the equation representing the proportional controller in time domain is mt equal to kCET. Okay, and in Laplace domain this equation will be ms equal to kCES. Now the transfer function of proportional controller Ks equal to Ms by Es, and this is equal to Kc. So if we take first order system, so let the transfer function of a first order process be Gs equal to K by tau s plus 1, and the transfer function of the proportional controller be Kc. Okay, so see, the forward part transfer function is given by Kkc by tau s plus 1, and the closed loop transfer function is Ts equal to Kkc divided by tau s plus 1 plus Kkc. Okay, so after simplifying this equation, we can write, after simplifying this term, we can write this. Okay, so here see, we put KCl is equal to Kkc divided by 1 plus Kkc, and tau Cl equal to tau by 1 plus Kkc, and these are the closed loop steady state gain and closed loop time constant respectively. So from this equation, we can note that an increase in Kc decreases tau Cl and speeds up the closed loop response. Now, if we calculate the steady state error for unit step input, then our steady state error ESS equal to 1 by 1 plus Kkc. So from this equation, we find that the steady state error decreases as Kc increases, and that is the system output will not exactly match the desired set point. The difference between the set point and the system output is known as steady state error or offset. When Kc approaches infinity, the steady state error becomes 0. But that is practically not possible. We can find from this equation that an increase in Kc speeds up the transient response and reduces steady state error of the system. For the first order and second order system, the roots of the closed loop system with proportional controller lies in the left half of the S-plane irrespective of Kc. But the system is completely stable. Okay, so for first order and second order system, the roots of the closed loop system with proportional controller lies in the left half of the S-plane irrespective of Kc, and the system is completely stable. But this is not the case for higher order system. For higher order system, as Kc increases, some of the roots of the characteristics equation may move towards right hand side of the S-plane and drive the system to instability. Okay. Now we will discuss about integral controller. So see, integral controller, basically integral controller is denoted by term I, capital I, in the PID controller. Integral controller increases the type number of the system by 1. Okay, we have already seen this in integral compensation, error compensation scheme. So integral controller increases the type number of the system by 1. Integral control overcomes integral control overcomes the drawback of proportional control by reducing steady state error to 0 without the use of excessive large controller gain. The time domain and frequency domain representation of integral controller is shown in figure 2.58a and 2.58b respectively. Okay. Now you take first order system with an integral controller, and let us consider the process, that means Gs equal to K divided by tau s plus 1 and Ks equal to Ki by S. Okay. Now the forward part transfer function of the system, see, the forward part transfer function of the system is given by Kki divided by S into tau s plus 1. Now if we calculate the steady state error for unit step input, then our steady state error is see ESS equal to 0. Okay, so see the steady state error becomes 0 due to integral action. That is, inclusion of an integral controller increases the type number by 1 and reduces the steady state error to 0 for a type 0 system. The integral gain Ki is taken to be positive so that Ki is greater than 0. The presence of integral action in a controller usually leads to an oscillatory closed loop system response. So the presence of integral action in a controller usually leads to an oscillatory closed loop system response, and sometimes it may lead to instability. Okay. Now we will discuss derivative controller. So derivative controller, sometimes called predictive controller. Okay. So see, derivative control do not affect steady state error but affect transient response. The output of a derivative control represent D. Okay, so the output of derivative control, that means D term in the PID controller, depends on the rate of change of error signal. The drawback of derivative control is that it amplifies the noise signal. Therefore, in real-time application, we cannot implement derivative action, but we use a modified derivative controller where the controller output is proportional to approximate differentiation of error signal. However, derivative control is essential in some real world control applications. For example, tachogenerator feedback in DC motor control is a form of derivative control. The derivative control can be represented as follows. In time domain, this is mt equal to kd d dt, and in Laplace domain, this is ms, and this is equivalent to kd s es. The output of a derivative controller is 0 when the error signal becomes constant. That is, the derivative control has no output when it is acting on constant signal. So derivative control cannot be used alone, and we always use the derivative control term in combination with a proportional term, that is called PD controller. Okay, so in this lecture I will discuss about all controller, that means PID controller, P controller, integral control, P means proportional controller, integral controller, derivative controller. Okay, thank you.